Howdy, and welcome to our first class video. Main topic for this one is going to be Blackbody radiation. But before we start into that, I'd like to say a few words about quantum mechanics in general, because that's the first topic that we will take up in the course. And it's kind of an unusual one, and so I want to give you all a bit of a rundown on how it differs from things you're more familiar with. All right. This text on the screen right now is a quotation from Richard Feynman, who's a fairly famous old physicist. Talks about what quantum mechanics actually is. Description of the behavior of matter and light, particularly on the atomic scale. Okay, so this is going to be a way to describe things on very small distance scales. There's reason to believe that the ideas of quantum mechanics in principle apply for macroscopic objects, but the fact is they really don't make any difference, and so we don't think of the everyday world this way. Okay, as it says, things on a very small scale behave like nothing you have any experience about. Okay, and that's why quantum mechanics is a peculiar subject. It seems to go against your normal understanding of the world around you. All right. In spite of this, quantum mechanics turns out to be the best way we have available to think about the behavior and properties of atoms and molecules, especially in their interactions with one another and with light and various other things on very small distance scales. Okay, and so for that reason, in the realm of chemistry, quantum mechanics was what gives us our best description of atoms and molecules, and helps us to explain how different atoms actually act differently and so on. Before venturing into some things, a little bit about some areas of relevance. Quantum mechanics is a fairly abstract thing. And in fact, when I first learned about quantum mechanics, there really weren't a lot of things that could be pointed to that said this was a real world application of quantum mechanics. That's no longer true. There are a variety of materials and devices, like the ones on the screen there, carbon nanotubes, which are used to produce electronic devices on very small scales. For example, transistors on the nanometer kind of distance scale, for example. Those are things that can be made, and that understanding how they function and figuring out how to assemble them really does depend on a detailed knowledge of quantum mechanics. All right. Lots of techniques, some of which you've used in other labs. Any kind of spectroscopy. If you've taken an IR spectrum or looked at one for anything in organic lab or anything like that, then you've been looking at things that rely upon quantum mechanics in order for them to do their job. Okay. And nowadays there's quantum computing and a whole variety of other things that are built directly out of understanding quantum mechanics. I put together a slide here which has a comparison of kind of the large world and the small world in one sense, or classical mechanics and quantum mechanics. All right. Classical mechanics, that's sort of normal physics. If you think about taking mechanics, your first physics course, you understand that you can apply sort of your everyday knowledge to things like that. Classical mechanics deals with things that are relatively large. Macroscopic objects is a good way of thinking about that. Quantum mechanics, on the other hand, its specialty is dealing with very small things, things that are more like the size of atoms and molecules. Correlated with those sizes, the objects in classical mechanics tend to be much heavier. Objects in quantum mechanics tend to have very small masses. Right? Where things get really peculiar is in classical mechanics, most of the variables we think about are what we would call continuous. So if you're talking about the speed of an object, there's no reason to think that speed can't take on any value that it wants. Right? If you're traveling at one speed, you could speed up by some infinitesimal increment, and that would be perfectly fine. The variables that you use can change and take on literally any value. In quantum mechanics, the name quantum mechanics comes from the fact that we say lots of properties are quantized. That means these properties can only take on a certain limited number of discrete values. So picture an energy that can be either one value or another. And you know examples of this. You know about energy level diagrams for atoms, right? If you've written electron configurations for atoms in Gen Chem, you said you have your 1s orbital and your 2s orbital and so on, and you don't have electrons with energies in between those. Those are quantized energies. There's a restriction on what values are allowed. Okay, it's a very strange phenomenon. It's something that's difficult to wrap your head around because, again, it's not like how the objects that are around you behave. It's not like if you're driving your car can go any speed it wants, right? You don't have to just transition from going 5 miles an hour to going 10 miles an hour. You have to pass through the speeds in between. In classical mechanics, we deal with things like Newton's equations of motion, right? In quantum mechanics, we deal with what is known as the Schrödinger equation, and we will come to that in a short while when we move into chapter 3 of the textbook. Classical mechanics is based on ideas like trajectories, right? When you do problems in your introductory physics class, you always say things like, well, if I know the initial position of the object and I know its initial velocity vector, I know the forces acting upon it, then you can put together a trajectory equation that tells you this is where it will be at every moment after that, right? And that's a sort of standard problem in a physics class. Quantum mechanics is about wave functions. Wave functions are very unsatisfying from a sort of intuitive point of view. Wave function is a mathematical function that is said to describe completely all the properties of, say, an electron in an atom, okay? Unlike being on a trajectory, the wave function is based on things that are probabilities, right? So my next bullet down there says classical mechanics is deterministic. Again, that means once you know the coordinates of something and the forces acting on it, you know everything about it. You can tell where it's going to be at any time later of your choosing. Quantum mechanics works on probabilities. So you cannot say, I know this electron is here right now, and I know therefore later it will be over there. Right? Sort of the classic picture of atoms as things looking like solar systems with a nucleus in the middle and electrons whizzing around them on orbits. That's not what atoms really look like. Okay, that's not how atoms actually behave. You cannot predict the location of an electron in an atom. Classical mechanics, because it is the rules that govern the world you live in for the most part, at least on the scale in which you inhabit that world, is intuitive. You have a feel for things, right? If you're doing a physics problem again and you get an answer that's ridiculous, you usually can tell, like, yeah, that doesn't seem right. I don't think that's what should have happened under those circumstances. It should have slowed down and not sped up or what have you, right? Quantum mechanics can be quite non-intuitive because, again, the objects we're familiar with don't tend to act like quantum systems. And so it's a sort of more of a struggle conceptually to make sense of some things in quantum mechanics very often. So the first chapter we're going to take up in the textbook is chapter 2. Chapter 1 is a review of sort of classical thermodynamics, and I have it on good authority that all of you have taken plenty of thermodynamics, and so we don't delve into that material. The purpose of chapter 2 is to just say, why did people make up this strange way of thinking about the world, right? What are the origin story for quantum mechanics? And that's our purpose in these first couple of videos, right? Quantum mechanics dates back to the earliest part of the 20th century. Right around 1900 is where various things started to be observed that led to this proposal that now is probably accepted, okay? Like a lot of things in science, the reason why people went to the trouble of making up quantum mechanics and why they came to believe in what you'll see is such a strange view of the world is because it was a way to explain experimental observations, right? So this is how science works. People think we understand something, then an experiment comes along that breaks the rules of whatever the old rules were, and then we have to make up a new model, right? If our experiment doesn't agree with the model that we thought was correct, then we have to adjust the model accordingly, right? The development of quantum mechanics represents a major upheaval in the modeling of how things work, sort of leaving behind classical mechanics and moving in a whole other direction. The first thing we're going to take up here, and it's partly historical, it's one of the first things that was noticed or that came to be observed that didn't follow classical rules, is what's called Blackbody radiation, okay? It's also a relatively simple one to understand. Warning, as we go through this set of slides, I'm going to flash by a number of equations. They're going to pass by pretty quickly. Most of them are not what I would consider important. I certainly don't expect you to be remembering them or anything like that. But they're here just to illustrate kind of how this idea arose. So we say blackbody radiation. That's a strange phrase. It's not something people talk about all the time. What it really means is just light or radiation being given off by any object as a result of its temperature, okay? There's a couple of pictures there that are things. The top one is just an electric stove burner, right? So if you have an electric stove in your apartment or your homes, you are familiar with that look where those are reasonably hot burners, so they're glowing red because that's the wavelengths of light that there's the most of coming off of the burner, all right? The picture on the bottom is actually an infrared image of a house, and people sometimes use those images to try and find places where their homes are leaking heat, say in the wintertime, right? Maybe not so much here in Texas, but in other parts of the country where the major cost is your heating rather than your cooling. We could do the same thing here, and you could find the places where your cold air was leaking out by doing something similar. And in there you can see, for example, that around the windows, the color is very different than around other parts of the house, right? And that's because those things are at different temperatures, reflecting the amount of radiation or of heat being lost through the different parts of the home, okay? What do people know? What did people know about this blackbody radiation? Back in the late 1800s, people knew that radiation was emitted, and they had models that told them pretty well what is the total amount of energy emitted, for example. All right. It turns out that becoming able to measure the spectrum, or the wavelength distribution of the light, is one of the things that caused this sort of beginnings of putting together quantum mechanics, right? And so the spectrum and the intensity depend on the temperature of the object, okay? The spectrum just says what wavelengths is there more of and less light being emitted at. And you can see again in the picture of the house there, the different colors in that's an image processed thing, but the different colors there represent different wavelengths of infrared light being the primary emission, okay? In the case of the stove burner, we know if you turn the burner off, it will look kind of black. If you could keep heating it up, it would go through a sort of a dull orange, go through some reds, and eventually, if it could get that hot, it would get moved towards white, right? The stove burner won't do that, but you're sort of aware that things do go through that color transition as they heat up. So dating back to 1879, as it says there is something known as the Stefan Boltzmann Law, which says that P, the total limited power density, the amount of energy coming off of our object, is given by that collection of terms, right? Where epsilon is a so-called emissivity, okay? When we say blackbody radiation, the classic definition of a black body, a perfect black body, is something that absorbs or emits all wavelengths of light equally. There really is no such thing as a perfect black body, but there are reasonable approximations. If we had a perfect black body, that epsilon term would be equal to 1, okay? The amount of energy radiated by a hot object actually does depend somewhat on the material that object is made of, and that epsilon term corrects for that. Sigma is just a constant, the so-called Stefan Boltzmann constant, okay? And it's on the screen down here with a rather peculiar looking set of units, but that thing just tells us, oops, I do that a lot, I'm afraid. That just tells us that's the proportionality constant that makes this thing work out. T is a temperature. Like anytime we're multiplying by temperature, it's got to be in Kelvin. And notice T is to the 4th power, so there's a strong dependence there, right? Our units on that P, they're joules meters squared per second, okay? And so that tells us that that's looking in, obviously, if the object is bigger, it's going to emit more total energy, and that's why the meter squared piece is in there. So here is an idealized black body, or a way we might realize one in the laboratory, okay? To be a black body, that means that you emit or absorb all incident light or outgoing light, regardless of the angle and regardless of wavelength, okay? So these are objects that they would not have a color to them, because if it has a color, that means it's reflecting or transmitting that color more so than others, right? And so the black body would appear black at normal temperatures, at sort of ambient room temperature, because the radiation being emitted would all be in the infrared region. Okay, that's why in that picture of the house, for example, it was taken with an IR camera. Gosh, night vision glasses work by looking at IR radiation, right? Because any people or animals or what have you that are moving around will be emitting infrared light, and that's what shows up in those particular devices. Okay, if we want to simulate a black body in the lab, the normal thing to do is to take a sphere or a cube and get it all enclosed, heat it up, so that you have a cavity inside, and you just have a small pinhole in it. Okay, so over here where it says window, that just represents a spot where we would have just an opening, a little hole cut in there, so that light would bleed out from there. Okay. The light inside would be reflected off of the surfaces, and that means that the amount of light leaving ideally is just a small portion of the light that's in there. So the object itself stays in thermal equilibrium as radiation leaves through the pinhole, and that's kind of why it's configured that way. That's not terribly important for our purposes. So the beginning of trouble in this black body, people think they understand this. Like a lot of things in earlier times in science, there's a model that works, and then people begin to become able to measure the spectrum of the emitted light. Okay, that requires that you have some decent sort of monochromator and detector, right? So a prism that you have some control over, and something that can measure the light in a reasonable fashion. Okay. If you do that, there's a graph on the screen right now which has Blackbody Spectra for objects at different temperatures, okay, ranging from 2000 Kelvin through 5000 Kelvin. In that particular range of temperatures, these are things where you would be able to see some amount of glow to the object. The visible spectrum is highlighted here, right? So this region marked as visible light. The only thing that's special about those wavelengths is they're the ones that humans can see, okay? And so, but that does give us some idea of what the thing would look like, okay? If I go down to the 2000 Kelvin end of this thing, that object would look red to a human eye, because there is more red light in there than any other visible color, right? As I move up through those, it would be drifting, still peaking in the red for most of those temperatures. By the time I get up to the hottest temperatures there, the 4,000 and 5,000 Kelvin temperatures, my object is gonna look fairly white. Right? Because at the 5000 curve in particular, I've got substantial amounts of light being emitted at all the wavelengths of visible light all across my spectrum. And so this is going to appear kind of a whitish to sort of bright yellow kind of color. 5000 Kelvin is actually somewhere near the black body temperature of the sun. And so that's a sort of just a relative calibration of what those things would be. Okay. Over here, I've got infrared light at longer wavelengths. I've got UV light here at shorter wavelengths, and you can see there's plenty of that being emitted as well. There's a dot on each one of these that labels the peak or the maximum in that curve. That peak wavelength, it turns out, follows an equation as well. And this is pretty much an empirical equation that just says the peak wavelength, lambda max, this is what's known as the Wien displacement law. It says that's just this constant on the top divided by temperature, okay? And that gives a reasonable match to where those peaks show up. All right. There's no particular underpinning theoretically to this constant, this number up here. It's just found because it fits the data, right? So if you measure those spectra at different temperatures, that thing makes the equation fit. So where does this light come from? What causes our black body to be glowing like this, right? And the explanation for this is, and in fact always has been, that it would be associated with vibrational motions of the atoms in the solid object, okay? That was true in a classical picture of this back in the 1800s. People certainly knew that the materials were made of atoms by then, right? Believed that idea, that those atoms are free to be vibrating with certain frequencies, and that's the origin of the light, right? That there be energy given off associated with that motion. And that's what's known, and if you read the textbook about this, it'll talk about oscillators or modes. That refers to just atoms vibrating at a particular frequency would be an oscillation or an oscillator or a mode, okay? The classical physics model of this would say that these oscillations should be able to occur with any frequency at all, that the frequency is not limited. The frequency of that vibration would be a continuous variable, right? And that all possible frequencies should contribute to what's being emitted, okay? Those frequencies I noted on the bottom of the slide are sometimes referred to as modes of vibration. We'll use that term more later on when we talk about vibrations in molecules and things like that. But don't let it throw you right now. When it says mode, just think vibration or vibrational frequency, and you'll do fine, okay? So that model says that the atoms can vibrate at any frequency they want, and there's no restrictions, no reason why some frequencies should be more likely than others, okay? If you do some physics starting from that proposition, it turns out you can put together what is known as the Rayleigh Law, which is the equation on the screen right here. Okay, this one, rho, the left-hand side, is the spectral distribution function. So that's in joules per meter to the fourth. Okay, that's got because of the wavelength to the fourth power on the bottom. Again, the units are a little bit peculiar. This is our first time of many meeting up with KB here. That is Boltzmann's constant, if you're not familiar with that. Gosh, Boltzmann's constant, a good way to describe that is it's the gas constant R, except per molecule instead of per mole. Okay, its value, as it says there, is 1.38 times 10 to the minus 23 joules per Kelvin. If you were to take R, which is 8.314 joules per Kelvin per mole, and divide it by Avogadro's number, you would get Boltzmann's constant. So that's what that number is, and it's multiplied by T. We will see that Boltzmann's constant times T many, many times over the duration of this course. And Boltzmann's constant has joules per Kelvin, temperature is in Kelvin, so that KT quantity is going to get us joules, okay? And then this thing, I note that I've got wavelength to the fourth under here. So that says it's a very strong dependence on wavelength. And this piece back here, well, wrong way. I'm sorry, I haven't done this for a while and my computer is out of control. This piece says that's the number of modes of oscillation within a given range of wavelengths, okay? So that's a classical prediction. It's based on just saying that the things can vibrate with whatever frequencies they want. That equation turns out to do a horrible job of matching the actual observed spectrum. Okay, if you look at that, because it's got wavelength to the fourth power on the bottom, that is not a function that will go through a maximum with respect to wavelength, right? If I flip back for a second to the spectrum, you can see we very definitely have peaks in those spectra, right? This equation suggests that there should not be a peak. It should just keep going up as the wavelength gets smaller. And in fact, that is what would happen in that equation, right? So this is what gets the rather dramatic name, the ultraviolet catastrophe up here, okay? If you take that equation and plot it for temperature, this is the 5,000 Kelvin equivalent of that. The dashed line here shows what the equation predicts. And the thing about it is this curve here would keep going up, and it would go up infinitely high, suggesting that at short wavelengths, there'd be infinitely much energy coming off of your object, all right? That says if you were to take the integral of that function, you should get the total amount of energy, right? And that goes to infinity, and that can't be right, all right? And so trying to explain how this thing should look says that this idea that it's just the vibrating atoms and that all the frequencies can contribute, that doesn't work, all right? It's not a reasonable prediction of what happens, and it just doesn't make sense, okay? That idea that instead of coming down after going through a maximum, which is observed experimentally, that amount of energy being emitted should just keep going up, that's kind of the first motivation for putting together a proposal that this vibrational energy of the atoms in the solid should be quantized. That proposal is due to Max Planck, whose name lives on in Planck's constant, which you've probably met up with in Gen Chem, if not elsewhere, as something that shows up when we talk about energies in atoms and that sort of thing. So what is the Planck model for this? The Planck model, the first quantum proposition really, says that these oscillations, these vibrations of the atoms in the solid, they can only take place with certain discrete energies. Okay, it's a very weird thing to propose because again, there's no real analog to this in everyday experience, but that the energy would be restricted to take on values that are just some integer multiple, n is just a whole number here, times h nu, right? Where nu is a frequency, h is what becomes known as Planck's constant, all right? The main essence of that proposal is that it says there will be a set of allowed energies and they would be equally spaced in energy. So over here, if energy increases as I go up, then this is an energy diagram, right? If the bottom one is the smallest possible energy, then I get multiples of that, 2 times it, 3 times it, and so on, right? The actual contributions of these different oscillations is going to be weighted by what is known as a Boltzmann equation. Essentially, that says as you go up in energy, the thing gets less likely. Lower energy states are more probable. Upper energy states are less probable. They're less populated, okay? You use that idea without expressing it that way when you talk about an electron configuration. When you say a hydrogen atom should have its electron in the 1s orbital, you're saying like the 1s orbital is so much lower in energy than the 2s orbital that they're effectively all going to be down there unless the atoms are really, really hot, right? And this is this Boltzmann equation down here. We will get to know and love that over the course. For now, we're just going to throw out there that's what this would look like. Okay, what does this say? It says that the vibrations at higher energies, which is shorter wavelengths, are going to be much less likely. If I go to high enough energy, they're just not really going to be able to vibrate at all unless the temperature is very high, right? Because this thing says the probability for being at a higher N here, right? This N is on the top, the energies are going up. Unless T is very high, then this probability is going to die off, right? So the low energy vibrations or low frequency vibrations are likely. They're going to be the only ones really that are important. If I go high enough in energy, they're not going to contribute to my emitted radiation. And that's what brings us back down on the long wavelength, or on the short wavelength end of that spectrum, because high energy is short wavelength, right? Take this model and we're going to do a little bit of math with it, all right? The total energy is just this thing, the P of EJ, that's just the probability of being in that vibrational energy level, right? So if I take the probabilities and multiply them by the energies and sum across all the possible states, that just says that'll be the total energy, right? If I went back to this one here, my bottom energy, whatever this energy is, I have 3 out of my 6 atoms represented there at that energy, then 2 and then 1. So my probabilities would be 3, 6, 2, 6, 1, 6. Then I multiply those by the energy. I'd get the total energy from that, okay? The average energy per oscillator or per oscillating frequency is given by the number written there, h nu times e to the h nu over kt minus 1. All right, that's just an equation that is developed and put forward in your textbook. It's the details of it aren't wildly important for us, so I don't want to spend a lot of time working through that. And our total number of modes is, we mentioned before that was this 8 pi over lambda to the 4th. That's the total number of vibrations. If we transform that into frequency, we can get to the result on the right-hand side there, right? That's based on saying that c, the speed of light, is equal to lambda times nu, right? And that gives you the relationship between d lambda and d nu, which would let us do that, that transformation. Okay, if we take those things and put them together, we can get to an equation down here, and this one says this is now an equation for this row of lambda. So this is telling me what the spectrum is going to look like, right? The energy distribution. And this form is in wavelength now. The one above it is in frequency, but the graphs that we have are in wavelength, so it's easier to look at it this way. It's got a wavelength to the 5th term down here, but now it's got a piece with wavelength in it over there. And this piece actually is, this function now is going to go through a maximum and come back down, right? And so that says, if we just say, what if this is the way that the vibrations work? We get to an equation that actually is a better fit to what is seen experimentally, right? If we take that thing and fit it, it turns out it is a very good match to what the spectrum looks like. Okay, and there's a plot coming up in a second, I believe, that's going to make that point for us again, one that's got the spectra at different temperatures on it. I'm flipping through to make sure that I'm right about that being going to appear. No, I'm not right about that going to appear, but we saw it before, right, where the solid lines that went through those spectra, they essentially are plots of this function, this Planck equation for the wavelength distribution, okay? It turns out that the earliest experimental value for Planck's constant was actually found by taking this equation here and fitting it, so not knowing the value of h, and just letting h be a floating parameter and making that equation fit the observed spectrum well, got the first proposed value of Planck's constant. Over the years, people came up with lots of more and more accurate ways to measure that constant. A couple of years ago, that number, Planck's constant, was actually redefined to be an exact number. There's actually a trend in measurement science and in the people that are in charge of unit systems and whatnot to define various things that we used to measure experimentally. And Planck's constant is one of those. The value down there on the bottom is the quote official value, and that is, as it says, it's an exact number, meaning there are no digits after the zero in there. Avogadro's number is another one that has now been defined to have an exact value instead of being defined as saying it's just the number of carbon-12 atoms it takes to make 12 grams. It is now a number that has just been declared to be equal to what was the previously most accurate measured value of that. Okay, so that's Planck's constant. The fact that that same Planck's constant has shown up in many other contexts since then and works in all of them is some reasonably good evidence that this thing has something going for it, right? This is a good explanation. This was proposed gosh, by now something on the order of 120 years ago, and the fact that it is still with us as a description of this suggests that it was in fact on target as a model for things, okay? Finishing out, I put one more slide here in the end that just points to another place where you can see the effect of this wavelength distribution, and that's astronomers categorize stars based on their sizes and colors, and those things correlate with temperature. Okay, and so the letters on there represent what are just different categories that astronomers use to label stars. You can see here that we have down here one that you can just barely see that there's any color there. There's a sort of a faint orange glow in the background. We go through some reds and oranges. We get to yellow. And then we get where they're white. That's again where we're in that range where we've got lots of light being emitted at all the wavelengths there. When it goes to blue on the far end there, that's because the peak has shifted and now there is very little emission in the red part of the visible spectrum, and so the part of the visible spectrum that is present is blue, and so we begin to see it as blue rather than as red light, as white light at that point. Okay, that's a fairly quick overview of the ideas of blackbody radiation. When you work on the first problem set, you will have a couple of things to do that deal with actually grabbing some of those equations and doing a couple manipulations on them. The reason why I do this part pretty quickly is just because, again, it's kind of motivational. It's just saying this is kind of the reason why this model that we're going to work with was put together. And so I like to start from there and to make clear the idea that these things originate in explaining experiments, right? Because that's an important point, is this is not something that people just made up because they thought it was mathematically fun. It's put together because it can explain observations, all right? In the next couple of videos, we'll talk about some other experiments from the early part of the 20th century that taken together kind of reinforce and really cement in our belief system the idea that energies of various small systems and of light itself turn out to be quantized and to obey the rules of quantum mechanics. Thanks.